Hello, so today we released the new version 9.1.12 and I'm going to show you some new features so you can discover it with me. So let's start with this wingfoil board, for example. We'll use this file to show you a first new feature, which is the possibility to handle the resizing of the depths of a V or a concave different ways. So if you look at this new version, when you check constant rocker proportion for the resize, you have three choices for the V concave resize, which is resize it with thickness, which is mean proportionally to the thickness. This will keep resize the wall slices homothetically, or resize it with a rocker, or none, which is don't change the depth of the V or the concave when I resize the board. And that was the default feature in previous versions. So let me show you. For example, if you look at here on this slice, the depth, let's go in inch. The depth of this double concave is 0.279. And if I resize it using known, and I change, for example, the length and the thickness of the board, you see the board is thicker, but the depth of this double concave is still the same. Okay, now if I undo, and now if I do the same thing but checking thickness for the V concave resizing with the same dimensions, you see that the wall slice is resized and the depth is now much higher. And if I resize it now with a rocker, and if I do the same, where I resize the rocker proportionally to the length, you see that the depth of the concave has changed, but only to a small value. Okay, so that's the first new feature. Now let's look at the plugs. Now you can see that the plugs appears in the curves list on the right hand side. So you have the thin twin here. When you click on it, it becomes yellow. It means that it's active. And you see there is another plug here which is not displayed. I can click here to display this plug, which is a sub handle. And now you can select these plugs from the list here and display all the properties of the plugs. For example, see these plugs, fin plugs are on the bottom. They are symmetrical left-right. You get the distance from the tail. Then you have these new parameters which are fixed to tail or fixed to nose, which are used when you resize the board. So if you fix to tail, it means that distance to tail won't change if you change the length of the board. If you click on nose, it means that distance to nose won't change when you resize the board. And if you uncheck both, it means that the X position of the plug will be resized proportionally to the length of the board. You have also the distance from the center axis or from the rail, and you can also choose to resize this Y position so that it's fixed to center axis or fixed to rail or known. Known means that the Y position of the plug will be resized proportionally to the width of the board. Then you have these parameters, fin length, toe, and tilt, which are for side fins. For foil boxes, there is no tilt at all, so it's all 0. You can also define the reference point of the plug, which is usually like the rear point of the fin. So that's something you usually define from for side fin on surfboard as well, because the rear point of the fin is slightly shifted from the center axis of the plug. There is still this auto positioning function, which used to be by default, which means that we stick the plug to the surface of the board, but you can uncheck this and change the way the plug is settled. And there is this new feature here, which is fixed to, which means you can fix the plug position to the position of another plug, this is used for foot strap insert, for example. Okay, and so you still have, when you select a plug from the outline view, this window here that shows the position of the plug and only a few of the parameters, and you can click more to have all the parameters. One thing that is new also is that when you select a plug, then you have the description of the plug, which is the same as in the plan mode, and you can move this description label so that in the plan mode it will be in the same position, because sometimes when you have too many plugs, all the labels are on top of each other, so you can move them from the design mode and make it clearer. So for example, if I add on this board like foot strap plugs, I can use the plug wizard, which is also in the size and parameters window, and use here to set like 1 foot strap at the tail and 2 at the front. This is the width of the foot. Press OK, and you'll see here it has added like 2 plugs at the tail, 2 at the front. They all appear here, so there is foot strap back 0, foot strap back 1. So foot strap back 0 is on the deck, it's centered, which means it's on the center axis, and it's not fixed to another plug. And the foot strap back 1 is centered as well, and it's fixed to foot strap back 0 with this distance, which is the width of the foot, and no tilt. So now I see if I select the rear box here, the other moves as well, but you can select the front one and move it independently, and then the other one follows. So you can change the width here. Same from them here. I can move them like this, and here see it's foot strap front 1 fixed to foot strap front 0 with this distance and 45 degrees for the tilt. And you can change it to 5 and press OK, and the distance is changed. And same for all these plugs, I can change the position of the label so that they are not all on top of each other, and you have a better view in the plan mode. Okay, so maybe we can use this board with that has a recessed deck design with a 3D layer to show you some new functionality on the 3D layers. So the 3D layers appears here in the curves list here. If you click on it, it becomes yellow as well. And if I click on the double arrow, I get the parameters. and I have a duplicate button. For example, if I want to create a hole for a reinforcement hard foam plate on the deck, I can duplicate this 3D layer and call it like deck length and set it as a constant depth 3D layer. So you can now change the type of a 3D layer that already exists. So you can use an existing one, change the type of the layer, for example, so, and set it like to 0.1 inch in depth, and maybe set it a little bit smaller. So 2.5 from tail, 2.10 up. Okay, it's here. Let's change the color so that you can look at it better. Okay, I can hide the rail curve. Okay, so that's better. Let's make it a little smaller. So you see, you will have a small depth on the deck that can be cut so that you can add a hard foam reinforcement after you have cut the board. And speaking of reinforcement, this new version has a function in the plan mode in menu plan flex distribution, and this mode allows you to have an insight on the weight and the flex of your board. So for this you need to define the density of the core. So let's say this board is like a regular EPS, it should be like around 20 kilogram per cube meters, and elastic modulus of let's say around 400 megapascal. Apply, and then if you do that, you'll see here you have the repartition of flex on your board. You have the volume. You also have the weight, which is here 1 kilogram and 1.8 kilogram, and the maximum elastic modulus of the board in Newton square meter. And you can also define the structure of the board using 3D layers. So for example, the deck reinforcement here, if you let the density and elastic modulus to 0, it means that it's empty. But if you click here and define the density, let's say for hard foam, it will be like 100 kilogram per cube meter, and 2000 megapascal for the elastic modulus. Then you will have the flex repartition of the 3D layer shown here and the total flex repartition. So you see you have the total weight, which is slightly higher, the maximum elastic modulus, and you can also show like a deflection test. For example, if you set the board on 2 support at like a 12 inch from tail and nose, and you apply like 20 kilogram, then you will see the maximum deflection here at x equal 37 inch, which is 0.016 inches. And it becomes more interesting if you add like fiberglass. So for that, you can add a new 3D layer, a constant depth 3D layer. Let's say, call it fiber deck. Thickness should be around 0.05 inch. And let's put it on the deck and extend it to the rail. Let's set it on the whole deck, so from 0 to 6.2. Okay. Layer larger than the board, so that it will just map the whole deck until the rail point. So you can see it if you zoom in. And then you do some tracing, you see the thickness. So then here you need to be careful on the order of the 3D layers. So the higher the 3D layer should be the external 3D layer. So for example, so you should apply a fiber deck first, and then the deck reinforcement, which means that you apply the, for example, deactivate the reinforcement. You have the 3D layer on of the fiber on the whole deck. Then you dig the deck reinforcement, and then we can add fiberglass on the bottom. So I duplicate this one. Bottom, so I put it on the bottom. I don't limit to the rail. Okay, so now you see you have the deck fiber that goes on the deck until the rail, and the bottom fiber that goes until the apex. You can actually make the bottom fibers go on the deck rail. For that, you go to bottom fiber and you set it so that the X curve map on the opposite side. For example, so now you need to set the external curve. So let's hide this, and I can copy the rail curve, for example, so that the rail curve, I select one point, do Control C, then select this curve, which is the outline of the bottom fiber, Control V, and that copied the curve. So I map this. So okay, let's deck center. Maybe I can just enlarge this so that it doesn't go past the recessed deck. Okay, so now you see that the bottom fiber goes on the deck rail until the curve you define. Okay, so now if I go to I need to define the density of the fiberglass, which should be about like 2000 kilograms per cubic meter and like 24,000 megapascal. Same for the bottom. Okay, and now you have the weight of the core, the elastic modulus of the core, the weight of the two layers of fiber, deck and bottom, with the elastic modulus, the total weight, we can also add the deck reinforcement, and you have the total weight, and also can see the max deflection when you apply like 20 kilo. You can see like if you apply like 70 kilograms, that the deflection is slightly increased, but still very small. And you can keep refining the structure like this, like adding more 3D layer for hardcore hard form reinforcement. Now that we are in the plan mode, maybe I could show you something that was already in the previous version, but it's still pretty new. It's hydrostatic stability. So if you define the immersed volume of your board, so let's say a guy is like 65 kilograms and the board is about 5 kilograms, then you will get approximately 70 liters underwater. And then when you define the immersed volume, which you can also do in the design mode, if you display the buoyancy line, maybe what we should do first is deactivate the 3D layer that renders for the structure, so that it doesn't change the general shape of the board. So I deactivate and hide all these 3D layers. It will make the not dead center because it's the shape of the board. Okay. So now we have defined the displacement volume, like the immersed volume, 70 liters, and we have the height of the buoyancy line here. We have the water line here in blue. And then in the plan mode, in the hydrostatic stability mode, we have two diagrams that show first the metacenter height. Basically, the higher the metacenter, the more stable is the board. And maybe you could read the tutorial about this. If you go to the plan chapter, you have this drawing here that shows that basically if the gravity center of the rider is below the metacenter, then the board is self-stable. But if it's higher than the metacenter, it's not self-stable, means that the rider needs some skills to stay up. And you can read all the description here. And basically here you see that the height of the metacenter is 7 inches, which is very small. So of course this board is not super stable. It's for wing foiling, so it's better with the wing. And in this diagram here you have the writing arm that basically shows the strains that will bring back the board when there is a heel angle. So the higher the writing arm increase when the heel angle increases, the more stable is the board. And usually at a special angle here, like here is 14 degrees, you reach the maximum of the writing arm, which means that past this angle, the board will flip. So that's some information that are useful for standard boards. And in this new version, we added the kappa drag approximation mode that shows the evolution of the drag with the speed. So it shows in blue here the viscous drag, and in red here is the residual drag, which is like the drag of the waves created by the board. But you must be aware that this is an approximation that comes from the kappa formula that has been made for sea kayaks. And if the shape of the board is too far from kayaks, and it will be out of the validity range, and it won't be valid at all, it will be like completely off compared with the reality. Usually then you get a warning in red like this. But well, it could still be an information if you want to compare two boards. And for example, if we open a file that is closer to a kayak, like a SUP like this, which is between a SUP and a kayak, and then we go for the kappa drag approximation, you see there is no warning, which means that you are in the right range for the shape of your board, and you see the evolution of the frictional drag in blue and residual drag in red and the total drag in black. And now what is interesting is if you want to compare this with another board, let's say for example I have another board which is slightly thinner and I can load it as a ghost. So it's thin, so it's actually, I don't resize, exactly the same board but thinner. I click on Ctrl plus L to lock the ghost so it doesn't move anymore, and you can compare the two shapes. It's very similar, only thinner. And if I look at the buoyancy line, so for the same displacement here, 110 liters, you will see that for the ghost board, like the thinner board, is slightly higher. And for sure, so it's thinner, so it means the buoyancy line must be higher to get the same immersed volume. And then if I go back to plane, you see the curve corresponding to the ghost will superpose. And you see here, it's interesting, you have a smaller viscous drag, but a higher wave drag for this board. And then you see finally the total drag is higher at high speed and smaller at small speed. And so in the plan map, you could also go to hydrostatic stability to compare the ghosts, and you will see, like as you could expect, the meta center is lower for the thinner board, so it means that it's less stable, and same for the writing arm. Okay, so what I could show you on this new version, last feature, which is in the CNC mode and concern boards with wings. So if I load this board here, that has wings here. So if you design the wings only from the outline curve, you'll usually have a king that will spread on the whole deck like this. So what you can do with Shape3d, well, you need a pro license for that. You can edit the curve corresponding to the deck 1 point here. So it's in yellow here. I can click here, choose edit. Okay, and then you see this curve becomes an editable curve. You can modify the control points, and I can remove the king here, set this tangent as a continuous tangent. And if I look at the 3D, you see it's better, but you still have a very small step. So this is actually due to the fact that this tangent here is continuous, and you have the constraint of this continuous tangent that will, I can press the T tab to see the tangents. So you see that the kinks of the rail will spread on the deck because the tangent has to be straight. So if you set this tangent as angular, then you don't have the continuous constraint anymore. And then you allow it to do a small kink when you go to the tail, but then you you separate the deck from the rail on this section, and you get a perfectly smooth deck. And so now if I go to the CNC mode, then when you cut that kind of board with wings, you have the toolpath that follows the outline, which means that the kinks will spread all over the deck, even though it's very smooth. And the result is a smooth deck, but still your machine will do all these kinks at each pass, and which is usually means that it will cut slower, and the result is not as clean. If you look at the finished preview here, you have these angles. So the new feature in this version is that you can choose one of the design curves of the board to be the guideline, the guide curve for the toolpath. So by default for the deck is the outline, but I could choose here the deck one curve as a guide curve, and I press apply. And now you see you still have the wing on the outline, on the outside rail, but then on the deck it's as smooth as the deck one curve you define. And if I look at the bottom, it's still following the rail curve, but here again I can choose the deck one curve as a guide, and you get something very smooth. So if I look at the preview, so the cutting will be as precise as before, but at least you can cut faster on the deck because you don't have these kinks. Let's hide the stringer. And same for the bottom. So that's a new feature which is maybe very interesting for CNC cut, as it's a final point of using Shape3d as always. So maybe I should stop here. There are of course many other small new features, small corrections as well, especially for Mac on Catalina. And of course, next update will come with new features. You will see. Okay, goodbye.